Welcome back. In this video, we are going to continue where the last one left off. So in the last video, we discussed how to create a shear diagram when you have point loads. In this video, we are going to do shear diagrams with distributed loads. So you have your beam right here, and you have your supports on either end, and then you have a distributed load, which you guys should know is a uniform load measured in pounds per linear foot or kips per linear foot. So when we did point loads happened at an instant. So the inch right before the point load happened, there was nothing going on. And then you have the point load occurring, and then the inch right after the point load, nothing is going on. It is only at that exact precise moment that there is a drop in the shear. That is why when we did the shear diagram, there was no slope. Since distributed loads are constantly applying more shear force per unit of length, the shear diagram is also constantly changing. So when we have distributed loads, because we are constantly adding more load as we move along the beam, the shear diagram is also going to be changing constantly. So it's not going to be a horizontal line. We're going to have a slope. Therefore, the shear diagram will have a constant slope for distributed loads, and the slope of the line is going to be equivalent to the uniform load, whether it be 50 pounds per linear foot, 100 pounds per linear foot, whatever the uniform load is, will now be the slope of the shear diagram for distributed loads. And for those who are in calculus, this is a real-world application of derivatives and integrals. We are doing essentially area under curve type math. Okay, let's go to an example. I always find that's the best way to explain a lot of these things. We have a simple beam with a uniform load of 1,090 pounds per foot, and the beam is 18 feet. And I will ask you, draw the shear diagram for this beam. So the first thing you would have to do is get the reactionary forces. And I just want to make a quick note because this was an area where a lot of people made mistakes last year. We are not replacing the distributed loads with the single point load in the middle for a shear diagram. If it's a distributed load, that should be handled differently than a point load. We only replaced the distributed load with a point load in the middle when we were doing reactionary forces. That's it. Okay, so first step is find the reactionary forces. Like I just said, to do that, we will replace the distributed load with a single point load in the middle, and then we will go right back to the distributed load. So we have the uniform load, which is 1,090 pounds per linear foot, multiplied by 18 feet, gives us 19,620 pounds of total load. Since this beam is symmetrically loaded, each side will take half, or 9,810 reactionary force per support. Okay, so here is what your finished shear diagram would look like. You start at 0, 0, 0, and the first thing you would see is a reactionary force of 9,810 going up. Then, because it's a distributed load, you are constantly having load going down. So you have a slope going downward. And the slope of this is going to be negative 1,090, which is going to be the uniform load right here. Meaning, for every 1 foot I move over, you are going down 1,090 feet. So over 1, down 1,090. Over 1, down 1,090. So on. And when I do that for 18 feet, over here, where x equals 18, I am now at negative 9,810. And then when I have the reactionary force over here of a value of 9,810, I go back to 0. So this is the completed shear diagram for a simple distributed load. Let's do another example. Let's do easier numbers. I have my distributed load is 100 pounds per linear foot, and my beam is 20 feet. So the total reactionary force per side is going to be 1,000 pounds. I assume you should be able to figure that out on your own now. And that means that I start off going up 1,000, and then for every 1 foot I move over, I'm going down 100. So my slope is negative 100. So up 1,000, over 1, down 100, over 1, down 100, so on, so forth. So let me ask you then, what would be the shear force at x equals 3? Well, if I'm starting at 1,000 and I'm going down 100 for each 1 foot, you can actually do this by doing the slope-intercept formula, y equals mx plus b. So if we have y equals mx plus b, my starting point is 1,000 minus 3 times the slope, 700 feet. Starting at 1,000, going over 3 feet, and for every 1 foot, I do 100. 1,000 minus 3 times 100 equals 700. And I could also ask you, where would the shear force be equal to 0? And I think a lot of you might realize that would occur right in the middle. Let's go back a few slides to the other one. It would occur right in the middle. The shear force would cross the x-axis at the halfway point. But if you want to see the math showing that, we can say y equals mx plus b. Y equals negative 100 is the slope, x plus your initial amount, 1,000. Solve for x, you get x equals 10 feet. And also note that at x equals 20 feet, you have a reactionary force upward of 1,000, bringing you back to 0. So this is going to be the direction probably. The general shape for all of your distributed loads shear diagrams. Okay, let's just take that a little bit further. So here is your beam right here. And the first force that you would see is an upward force of 1,000 pounds at the reaction. So now we are at y equals 1,000. And for every 1 foot we move along the x-axis or the beam, we move down 100 pounds of shear force. So we go over 1, down 100, over 1, down 100, over 1, down 100. And we keep doing that. And this drawing is to scale. And we see that when we get over here at x equals 20 feet, we are at negative 1,000. And then the reactionary force would bring you right back. And here's your finished product. Okay, so now we will analyze the shear of a beam that has both point and distributed loads. So up until this point, we've only done either only point loads or only distributed load. What happens if you have both? So when there is a distributed load, the shear diagram will go down at a slope. And again, the slope is going to be equal to the amount of kips or pounds per foot. And then when we have a point load, we will immediately drop the shear diagram by that amount. Let's go to an example. I have a distributed load where I have a simple beam of 20 feet, and then I have a distributed load of 650 pounds per foot, as well as a point load right here. And I give you the reactionary forces right here. I could just as easily or just as commonly ask you to solve that. Okay, so now we will start with our shear diagram right underneath it. And the first thing you would do, we start at 0, is go up your reactionary force. I would go up 9,300 pounds. Then as I move down, I will be dropping down 650 pounds every single foot until something else happens. In this case, this would be the next thing that would occur. So I'm going to be dropping 650 pounds per foot up until 6 feet, where at that point I will drop 4,000 pounds. After I drop 4,000 pounds from there, I will continue dropping down at a slope of 650 pounds per foot all the way until I get to x equals 20. Once I get there, I should be at negative 7,700, so when I go up the reactionary force of B, it brings me back to 0. So without calculating values, let's just try and think of the shape. I want you to kind of, pause the video and think of the shape that this should be. visualize the shape, and then we will do numbers. So this is the general shape that I would hope you could have envisioned. Again, you're going up, and then you're going down at a constant slope. Right at 6 feet, you're dropping down an amount, then you're continuing at that slope, and then at the end, you will go back up the reactionary force back to 0. Now let's add some numbers. Okay, so I go up 9,300. Then I'm dropping down 650 feet for 6 feet. So if I'm dropping 650 feet per foot for 6 feet, that gives me 3,090 pounds that I'm dropping down. I don't know what the math is right there. I guess that would be 5,400 right here. Right here is 5,400. And then at that point, I'm dropping down 4,000 pounds. So 5,400 minus 4,000 gives me 1,400 pounds right here. Then I will continue dropping down at 650 pounds per foot for another 14 feet. So if I do 1,400 minus 650 times 14, that'll give me negative 7,700 pounds. Ah, there it is. Oh well. Okay. And then I think this is the last slide. Let me go ahead to know my timing. Okay, we have 3 minutes to do this. Don't look, don't look. Okay. I may also ask you where along the beam the shear force is equal to 0. And again, those in calculus, you'll actually find this is going to be a maximum or a minimum for the next unit, but we won't get there yet. You might want to know where along the beam the shear force is equal to 0, which would occur right where the x is right there. So I'm not necessarily finding x. I would have to be doing 6 plus x. I want to know where this point is. Now, you might be tempted to say, oh, it's just, 5 units across, so whatever a unit is. But it's not quite that easy. We actually have to do a calculation. But all we have to do is slope-intercept calculation. Y equals mx plus b. So this time, when we're doing y equals mx plus b, we're just going to analyze this portion right here, just this line right here, a linear line. So we have y equals mx plus b. Y is equal to the shear force at a given point. X is the horizontal distance, and b is the starting shear force. So I know that the shear force at that instance is 0. So y is going to be equal to 0. The slope is going to be the negative 650. The x is what I'm solving for, and b is where I'm starting at, which is going to be this instant right here. Note the negative slope, and we will pretty much always have negative slopes when we do this because the forces are going down. We solve for x, and we get x equals 2.15. Now that's not the finished answer. That's just saying that x right here is 2.15. So again, the question was, where along the beam is the shear force equal to 0? The final answer would be 8.15. The 6 right here plus the 2.15 right here. So right along the beam, 8.15 feet away from point A is where the shear is equal to 0. And next lesson, we're going to be doing moments, and we will find that where the shear force is equal to 0 is where we have a maximum moment. All right, that's it for this video. Of course, always message me or email me or Google Hangout message to ask any questions.